So actually, in these two papers by Rudakov, this is a very old paper, almost 50 years ago. So he studied simple continuous modules of the Lie algebras of Cartan type WSH over formal power series. So because he used topological words, continuous, and the algebra are not over Laurent polynomials instead, and he used algebras over formal power series. Essentially, those modules are restricted modules, and he determined, to some extent, he determined those modules, or interpreted those modules as induced modules or some other level one modules. Okay, yeah, more or less, this is known. And now let's recall some familiar Lie algebras. Yeah, the Virasoro algebra, I use VIR. But the Virasoro algebra is an infinite dimensional Lie algebra with basis C, Dn, n is running over all integers with the Lie brackets. C is the center, and this is dm dn is equal to m minus n, dm plus n plus the central part. Okay, we know this is the universal central extension of the differential operator algebra of degree, I would say degree 1. Yeah. And then we have, let me give you this mirror Heisenberg-Virasoro algebra. I use D to denote this algebra. This algebra has a basis dm hr, C1 and C2, m running over integers, r running over half integers, not integers, just half integers. And subjected to the brackets, the first one is the Virasoro algebra, and this is the twisting action. The dm on hr is just the negative r times hm plus r. And for h, this is the twisted Heisenberg algebra, because the indices, we don't have h0. The indices are all half integers. C2, C1 are the centers. Okay. Yeah, this is the so-called mirror Heisenberg-Virasoro algebra. Now we have the Heisenberg-Virasoro algebra. So I use detailed. So very similar to the mirror Heisenberg-Virasoro algebra. The difference is only the Heisenberg part, the indices are all integers. The mn are all integers. Yeah, you have, the definition are identical. The definition is identical. So just all the indices are integers. So actually, you can consider the mirror Heisenberg-Virasoro algebra as a sub-algebra of this Heisenberg-Virasoro algebra. Yeah, say for example, if you take the indices for D as all even integers, and more or less you get the mirror Heisenberg-Virasoro algebra. So we're going to study all those algebras, and to start off, and we need some sub-algebras. Basically, I will mainly talk about this mirror Heisenberg-Virasoro algebra. Okay. We have where are the, sorry. Oh, it's backward. Sorry. Yeah. So here are some sub-algebras. The M are integer, non-active integers, and all integers. So we define this dmn. So that means the index of m, index of d bigger than or equal to m, the index of h bigger than or equal to n, or plus plus, yeah, plus half. So like this dm infinity, that means, you know, the Heisenberg part, yeah, we have all the Heisenberg part. So the Virasoro m, where are m, those are, you know, the index for d is always bigger than or equal to m. So they all include the centers. If I use where r bigger than or equal to m, then that means, you know, we don't have this center. Okay, yeah, we need those definitions. I will remind you of those definitions later. And we have more. This is where r smaller than or equal to 0. That's all the negative d negative i's. So where r plus, this is basically where r bigger than or equal to 0, right? Well, and c. No, this is where r sub 0. So Hn, we include the center. This is from bigger than or equal to n. Okay, not equal to n. Yeah. So this h bigger than or equal to n, we don't have the center. Yeah, those are all the subalgebras we're going to use. Okay. Okay. We need some other definitions. Recall those definitions. The L is a Lie algebra, V is an L module, X is an element in L. If for any small v in V, we have a positive integer n, so that x to the power of n acts on V is equal to 0, then we say that x acts on V locally nilpotently. If for any small v in V, this space x, the powers of x acts on V, the space span of all those elements is finite dimensional. Then we say x acts on V locally finitely. The action of L on V is said to be locally nilpotently. If for any small v, we can find a positive integer n, so that n elements from L act on V is equal to 0. Yeah, this n depends on the vector. Okay. So the action of L on V is said to be locally finite if any small v can generate a finite dimensional L submodule. Yeah, that is those are the standard definitions. Well, if W is a module over the mirror Heisenberg-Virasoro algebra, on which C acts as a complex scalar small c, C1, yeah, small c, and we say that W is of central charge C. If W is a module on which C2 acts as a complex number L, we see W is of level L. So this level means for the Heisenberg algebra center, central charge for the Virasoro algebra center. Okay. Now let's first look at the simple restricted modules over the Virasoro algebra. Actually, this is known. So in this paper, Mother Truk and me, so we to some extent we classified all simple restricted modules over the Virasoro algebra. So first we constructed those modules. Say any simple restrict, this is not this is the classification. Yeah, any simple restricted Virasoro module is a highest weight module or isomorphic to this induced module for a simple where our plus module V, such that for some k, this is a positive integer, not including 0. Dk acts on V injectively, and di v is equal to 0 for all I bigger than k. So here we have all the simple restricted Virasoro modules, Virasoro modules, the high-speed modules or induced modules satisfying this condition. Well, from these two conditions, you can see this V actually is, say, if you consider this Virasoro plus, this one, it contains center and all the elements D0, D1, D2, dot, dot. You see, V actually is a simple module over a finite dimensional solvable Lie algebra. So if you say, for example, if you take k to be the smallest number 1, that means D1 acts inductively, and all this V0 actually is a module of the two-dimensional algebra D0, D1, okay, solvable Lie algebra. And well, certainly to classify simple modules over finite dimensional solvable Lie algebras is really tough, actually. Yeah. So far, we only know the classification for, I call it for A2, that is spanned by D0, D1, and sorry, that is A1, and A2 spanned by D0, D1, and D2. So we don't have the classification for A3, four-dimensional solvable Lie algebra spanned by D0, D1, D2, D3. Okay, now let's look at the modules. Yeah, first, well, because we have the Heisenberg center and the level, we consider it in two different cases. Yeah. The one result is in this preprint. So here we determine all simple restricted modules with 0 level. Yeah, let V be a simple D0 negative n module for some positive n, positive number, positive integer n, and C. This is yeah, the level is 0. The central charge is C. Yeah, C can be 0, but it could be anything. Assume there exists an integer k bigger than or equal to negative n, satisfying the following two conditions. So the action of hk plus half on V is bijective, and for bigger indices, we have 0. So hm plus half V is equal to 0, and dm plus nv is equal to 0. But actually here, we don't require dn, injective or not. Just like it can be d, say d dn minus 1 could be V could be 0. We don't care about that. Then the induced d module is simple. Okay. So this d0 negative n, this is part of the Heisenberg mirror, the mirror Heisenberg-Virasoro algebra. So starting from d0, d1, d2, dot, dot, dot. And this h for Heisenberg part, we have h sub negative n plus half, and h negative n plus 1 plus half, and those kind of elements. Okay. Yeah. So the induced module in this case, yeah, is always simple. Let me see here. This n, keep in mind, this n is always positive integer, yeah, bigger than or equal to 1. Okay. Yeah. Yeah. This is a kind of construction of some simple restricted modules over the mirror Heisenberg-Virasoro algebra of level 0. Now here is the classification. Okay. Every simple restricted D module over the D is the mirror Heisenberg-Virasoro algebra. Yeah, every simple restricted D module of level 0 is isomorphic to a restricted VRR module with the action of H on S is 0, or S is the induced module. That is what we explained just in the previous theory. So here we have the highest weight module, right? Because see here, we have the Virasoro restrict simple. I should say simple. Yeah, it's clear. Simple restrictive Virasoro module. We have the classification, so we don't care about that. And we have two different classes of simple restricted modules over the Heisenberg-Virasoro, the mirror Heisenberg-Virasoro algebra. So this one over Heisenberg over Virasoro algebra or the induced module. Okay. Yeah. So that is this is for level 0 restricted module. Similar, yeah, the same thing applies. I mean, say for this module V, actually this V is a simple. If you look back, look at this V. This V is a simple module over a finite dimensional solvable Lie algebra, because here you model most H, you model most N. The only part, I guess, here is only the dimension is maybe here this is M. Sorry, this is here you have M, here you have M at most 2M plus 1. Yeah, the dimension. Yeah. Okay, now now we consider non-zero level restricted modules. Okay. If V is a Virasoro module, V is a module over the Virasoro algebra, then V can be easily viewed as a D module by defining the action of H trivially. So yeah, the resulting module is denoted by V to the power of D. Well, D is our mirror Heisenberg-Virasoro algebra. Yeah, this is from Virasoro module, we get mirror Heisenberg-Virasoro module. And also so here I have a restricted Heisenberg module. Well, this is, do you remember we use this script H to denote the twisted Heisenberg algebra with half index. We don't have H0. So this H is a restricted module over the the twisted Heisenberg algebra. Non-zero, yeah, this is the action is non-zero of the center. Then we use the vertex operator defined by Franco-Lebowski Muirman. We can make this H, module H, into a D module by those maps, say Dn X like Ln and those operators. Yeah. So those operators, you have an infinite sum like Slavas used, if you act on elements in H, this is finite sum. This is finite sum, because for most positive HK, the action on H is 0, because this is locally. This is a simple restricted model, may not be simple. Yeah. So we have HD. We have two different modules, constructed from other algebras. Now basically, I'm going to talk. The results I'm going to talk is from this preprint. Okay. Let me give you some such modules. Okay. This one. So here K is a positive integer, and is an integer. K bigger than or equal to n. And let V be a simple D0 negative n module with level L non-zero, such that we have a L non-negative integer satisfying both conditions A This h k minus half acts injectively on v. H I minus half on v and dj on v is 0 for all I bigger than k, j bigger than L. Then the induced module from d0 negative n to d is a simple d module if one of the following conditions holds. First, k is equal to n, L bigger than or equal to 2n, and dl acts injectively on B. Second condition, k bigger than n, k plus n bigger than or equal to 2, and L is equal to n plus k minus 1. So here, this k is always bigger than or equal to 1. We don't, yes, this k is always bigger than or equal to 1. Yeah. So here we constructed some simple restricted modules. Simple restricted module. Those are simple restricted modules. The level is not 0. Now we can have all the simple restricted modules over the mirror Heisenberg-Virasoro algebra with level non-zero. So here is the result. Let S be a simple restricted module over the mirror Heisenberg-Virasoro algebra D with level L non-zero. Then S is isomorphic to H to the power of D, where H is a simple restricted module over the Heisenberg algebra. 2. S is an induced D module from a simple restricted D0 negative n module for some positive integer n. Or S is isomorphic to U to the power of D tensor H to the power of D, where U is a simple restricted module over the Virasoro algebra, and H is a simple restricted module of the Heisenberg algebra H. So we have 3 different types of simple restricted modules over the mirror Heisenberg-Virasoro algebra. Okay. Now this is, if you take a closer look, we know, say, for the mirror Heisenberg-Virasoro algebra, we know all the simple highest weight modules. And this is quite different from highest weight case. For highest weight modules, we only have case 1 and case 3. We don't have in case 2. Yeah. But actually, at least later, I will give you some examples that belong to case 2, not case 1 or case 3. Oh, how come I have this one? Sorry. Yeah, I said this is different from highest weight case. Let me see. Okay. So here I have another roughly. This is the classification for simple restricted modules over the mirror Heisenberg-Virasoro algebra. Okay. Now actually, we have a better characterization for the condition to be restricted module. This is I think this is an interesting result. So let S be a simple module over the mirror Heisenberg-Virasoro algebra D, such that only one dn, you only know one dn acts on S locally finitely for some n positive. Then S is a simple restricted module over D. So you don't need to verify all positive n. You just find one dn to see whether this element acts on S is locally finite or not. Then you can conclude the whole module is restricted. Okay, yeah, I'm going to talk about the real A part. So here, yeah, this is I use detailed. Do you remember I used detailed I use this one to denote the the Heisenberg, not mirror, the twisted Heisenberg-Virasoro algebra. So all the indices are positive integers. So let's consider the subalgebra. I use P, so C1, C2, DM, Dn. All those m's are positive. Okay, those m's are positive. Oh, zero, positive 0. It's kind of the Borel subalgebra. Yeah. So L1, L2 are complex numbers, and then certainly we can define one-dimensional P module. Yeah. So and then we have this VL1, L2 induced module, and this is actually the Wolmer module, right? The Wolmer module. Yeah, it's the highest weight module over the Heisenberg-Virasoro algebra. Okay. We have the highest weight vector. We use one that is one tensor this element. Okay. And then we can define the following fields acts on this highest weight module. Those operators Hn, Hz, and Dz. Okay. And we use this notation to denote the universal Virasoro vortex algebra of central charge C generated by the Virasoro fields, say Lz. Okay. Now, for the Heisenberg, let's use this Lm to denote the Heisenberg vortex algebra of level L. Actually, level L generated by the Heisenberg fields. This is the Heisenberg. Yeah. So here this M running over integers. Okay. Certainly we require the level non-zero. Then ML is essentially the same with M1. So over Heisenberg algebras. Okay. So ML contains a Virasoro vortex subalgebra. We use this one. Later we see is1. Later we use V to the power of C. So we have those Virasoro fields. Okay. Those normal. Those are the normal order. Okay. If you take, we have those specialize this event. We have those operators, H, Heisenberg M. Okay. And now we have the following result. Okay. So for this L2, we have a vortex subalgebra. This V1, L2. If L2 is not 0, so L2 actually, L2, what is our L2? Okay, L2 actually is the Heisenberg part center. This is essentially our level, the level of the module. So we have the following isomorphism of vortex algebras. This where our C tensor ML2 is isomorphic to this V to the power of L1, L2. Okay. And because here we have center for this C. Here we have this C. In order to have the center C here, this C should be L1 minus 1. Okay. And we have those relationships between those operators, and we have this isomorphism. Okay. Now, for the modules, not yet there. Yeah, this is for the Heisenberg algebra, over the Heisenberg algebra. Okay. And we use this V to the power of C to denote this vortex algebra. Okay. Now we have to take a automorphism theta1 of order 2 of this algebra M1, satisfying this condition, and we can extend it to the whole algebra. And we use this evolution And this is a standard evolution. We use this evolution, and then we can characterize all the simple twisted, twisted modules. Okay. Now, the following two statements are equivalent. Oh, more or less, yeah. We have both of them. So assume that W is a simple restricted D module of central charge L1 and level 1. Yeah. Then W has the unique structure of a weak, simple, theta twisted V to the power of C module generated by the fields. And those are standard fields. Yeah. That means, from simple restricted D module, we get weak theta twisted module for the VOA. Okay, for the VOA. Now, conversely, assume that V is a weak, simple theta twisted V to the power of C module. Then W is a restricted D module of level 1. Okay. So because we already have the classification for simple restricted modules over D, and also we have the classifications for weak, simple, twisted modules over this V to the power of C. Okay. I'm going to give you some examples. Yeah, quickly. I started with some modules over two-dimensional solvable Lie algebras. Solvable Lie algebra. Yeah. This paper is an older paper by Block. So B is the two-dimensional solvable Lie algebra with basis HC with the bracket HC bracket is C. Is E. HE bracket is E. And C1, C2 non-zero, C1, C2 complex numbers with C2 non-zero. We take this alpha. This is a polynomial in S and T. Yeah, it's in this. This is the ring. This is the fraction field in T, and then we take the polynomial ring over this field. Now clearly this alpha is irreducible in this ring because the degree of S is 1. Okay. Then we construct this vector space. This vector space actually is isomorphic to what is A0? A0 actually is A0. I didn't explain it. A0 is the associative algebra generated by T and S over C. Over this intersection. This K alpha, this is the left ideal. A0, that is, A0, this should be the universal geometric algebra of B. Okay, I use T and S. Yeah, let's see. What is the bracket T and S? I think T. I don't have the bracket T and S. They're not commutative. T and S are not commutative. Okay. I deleted it, but anyway. So we have the concrete action. I have this vector space. Now I have the actions. The H action like this E action like this. E is just the multiplication by T. So H is this weird operator. Then on this vector space, we have a B module structure. This is a irreducible module. Okay, this is irreducible module. Then we make it. Yeah, we make this W prime into a D00 module. So C1 acts on C1, C2 acts on scalars, C1, C2. D0 acts on like this, negative half H acts on this FT, and H half like E times FT, and all others 0. So we made this one into a D00 module, and then we can induce. we can induce. This is a simple D00 module, and use our auxiliary established, and basically, we will have this induced. Well, first we induce one more step from 0 to -1. And this is you can easily see this is a simple module over that one, because you only consider the Heisenberg part. And then you introduce it to the whole Heisenberg, mirror Heisenberg-Virasoro algebra. You get this irreducible restricted module. But actually, this S is not a tensor product. It's not a tensor product. It's not a tensor product D module over the mirror Heisenberg algebra. Now, here are some explanations, but I don't want to get into details. So we use something else. Yeah, this is one example. Do I have, how much time do I have? I have 2 minutes. Kailash?
Yeah.
Okay. Yeah, let me quickly, I want to give you maybe one more example. Say here I have, maybe let's look at the, I have, so I have this A, B, C, C1, C2, those are, scalars. I guess this one is not star. That is the mistake I made. Yeah. So we define a one-dimensional D11 module. Say this C1, C2 scalars, and C2 is not 0. Okay, this is true. The C2 is not 0. Okay, D1, those are scalars. D1 and Dn are all zeros. Actually, this is like a Weidiger module, something like Weidiger modules. Say A, B, C2 are non-zero. This C1 can be anything, and then we can induce it to. Yeah, this is let's see. This is a D11 module. The index D bigger than or equal to 1, H bigger than or equal to 1. Yeah, and then we induce it to D00. Yeah, you can easily show that the induced module is irreducible over D00. And then you can induce it further. We get a simple restricted D module. This is another simple restricted D module. Now, in order to use, well, this module actually, this module is a simple restricted module over the mirror Heisenberg-Virasoro algebra, but this one cannot be written as a tensor product module. That is what so you see this, this module, this S, this module, this U hat, it's not a tensor product D module. Yeah, it is a simple, D module, but not a tensor product. Okay, thank you.